Good morning. We are heading into another chapter of Thermodynamics, chapter 19. This chapter 19 is talking about, apparently, what's called the first law of thermodynamics. And again, if you guys ever end up on the game show Jeopardy, these are going to be useful things. These are questions that could come up. What is the first law of thermodynamics? And it's energy conservation. It says at the level of individual atoms and molecules, energy still is conserved. And so we can look at all the potential energies, all the kinetic energies, and we can watch the energies shift back and forth between different molecular systems. Right now there's a fire going on, which means it's a chemical reaction, right? Everybody's sitting around the chemical reaction, enjoying the chemical reaction taking place. And as a result, chemical potential energy is getting converted into kinetic energy of the molecules. The molecules coming out of that reaction have a lot of kinetic energy, and then that kinetic energy is transferred to the surrounding molecules. Everybody's sitting around close. Everybody's, whenever there's a chemical reaction, people sit around that and sit close, and they go, what a beautiful chemical reaction. And the energy that's being generated, both through the light that's being generated and then just the molecular motion that's being generated, propagates through, and people experience the warmth. They experience their own molecules moving a little faster by sitting next to the exothermic chemical reaction. And the picture is absolutely beautiful. I mean, this looks like a lot of fun. We're out backpacking, out in the Sierra Nevadas, really pretty. Okay, so it's a good picture to represent energy conservation. Now there's a lot of stuff in chapter 19, so I gotta stop talking about these pictures and get moving with the topic, so let me do that. First of all, it says we often speak of heat as if it were some kind of material that flows back and forth. What we call heat is really just molecular motion. And what we said statistically happens is if some molecules have a lot of molecular motion and they run into other molecules, that molecular motion gets transferred. So we think of that as a transfer of energy from one to the next. Now, the unit that they bring out for heat is calorie, and I immediately cross that out because that's not our standard unit of energy. Our standard unit of energy is a joule. It does turn out that 1 calorie is the heat needed to raise the temperature of 1 gram of water 1 Celsius, but we're not going to be working in calories, we're going to be working in joules. It turns out that 1 calorie is the equivalent of 4.186 joules of energy. So again, we don't need the calorie. Definition of heat. Here we go. Here's another attempt. Heat is energy transferred from one object to another due to the difference in temperature. Now, I want to restate that in terms of molecular kinetic energies or molecular motion. So I've got samples of molecules. One is at a higher temperature than the other. That's really just saying there's more kinetic energy on average. Now, if you mix a bunch of molecules together, if you put them in contact, the ones with more kinetic energy, eventually the more kinetic energy will get spread around as a result of collision. So that energy, we say, gets transferred, and we end up with a statistically more likely distribution of the energy. Now, that doesn't mean every molecule has the very same amount. We saw in chapter 18 there are very definite formulas and very definite reasons and principles behind how the kinetic energy is distributed in a collection of molecules. So if that doesn't sound familiar, go back and take a look at chapter 18. We're going to work, not calories again. Okay, so we're going to have some ice cream and cake. Which I don't think that's throwing caution to the wind. Ice cream and cake sounds pretty good. Let's say that we have some ice cream and cake and it's listed as calories. Well, of course, the first thing we're going to do is convert that into joules. Now, when they say the ice cream and cake is 500 calories, those are kilocalories, which means it's 500,000 calories, so it's really 500,000 calories. And then for each calorie, it's like 4 joules. So we're looking at something like 2 million joules of energy. So the ice cream and cake is 2 million joules, or about 2 megajoules, or 2,000 kilojoules of energy. So that's what we're going to say is 2,000 kilojoules. Now, the energy in the food is what we call chemical potential energy, and that's taking different compounds and rearranging them. So you guys know from your biology classes and I want to say molecular biology classes, that these compounds are largely carbohydrates and lipids and proteins, and that when you metabolize those, what you end up with is a lot of energy. You run reactions with oxygen, and you generate things like water and carbon dioxide and urea, and these compounds have lower potential energies than those compounds. So the way the chemical bonds are structured, these have lower potential energy. And that means energy is converted into kinetic. So during processing the food, there's energy available. Now, if you're processing the food, you don't want all the energy just to go into kinetic energy. You don't want to just become a bunch of thermal energy and warm up. That actually gets linked into mechanical types of energy. So that enables you to move, for example. That can operate your muscles, it can make your heart muscles operate. Now what they're saying is, what would happen if we took this 2 million joules of energy and we used all of that energy, 100% efficiency, to climb something, to climb a mountain or a hill. How far would 2,000 kilojoules take us? And we could say, all right, we can take all that energy, all the potential energy in those compounds, and run these chemical reactions and somehow take that energy and convert it to mechanical energy very efficiently. That would be enough energy to climb a 3,000 foot mountain, 3,000 meters. That's like 10,000 feet. Hey, it was just some cake and ice cream, right? But there is enough energy stored in there, specifically running these chemical reactions. So when we say how much potential energy is there, we have to do that in comparison with, once the chemical reactions are run, now what was the difference in chemical potential energy? All right. And this is all, okay, and the other statement down here, the chemical potential energy has to do with how close the electrons are able to get to the protons. So it says that in water, carbon dioxide, urea, the electrons on average are closer to the protons in the nucleus, and that means that there's a lower potential energy, and that potential energy drop allows us to release that energy to be used in other ways. Now, if you're running a bunch of metabolic processes, you're probably generating a bunch of ATP molecules. You're running the processes through the Krebs cycle, you're running these compounds through different metabolic cycles, and then you're running phosphorylation, where you're generating a bunch of ATPs using oxygen to run those reactions. And those ATPs could be used just as thermal energy, but more likely the ATP molecules are going to be used to operate other chemical reactions, such as contracting a muscle. All right, and that's the idea. We're going to do a bunch of ATPs to contract muscles and climb this mountain. All right, let's get back to individual samples of molecules and ask about their, what we call internal energy. So the sum total of all the kinetic and potential energies of molecules in a sample is referred to as its internal energy, or its thermal energy. Now, okay, here's an object, here's a book. How much energy does this book have? You go, well, we'd have to go and look at all the individual molecules, add up all the vibrational energies, any translation or rotational energies, and then we would have to add in the potential energies. Now, the potential energies are negative, so we could take the kinetic energies and subtract off the potential energies and find out what the sum total is. That would be referred to as the internal energy of this sample, and that's because the energy is internal to the atoms and the molecules. Now, it's also referred to as thermal energy. Is there a way for me to estimate how much thermal energy is in this object? And I don't know about you guys, but I have internal energy sensors built into, well, everywhere. So I can touch this book and I can go, yeah, I think there's a fair amount of kinetic energy in those molecules. How did I know that? Well, when I touched this with my hand, it didn't feel cold and it didn't feel especially hot. It felt kind of room temperature. Now, that's enough that it should have a fair amount of kinetic energy, right? So I have thermal sensors that can tell when I touch something, is thermal energy being transferred into my hand or is it being transferred out of my hand? And that allows me to at least estimate how much internal energy a substance has. All right, let's see. Temperature, quick review. Temperature is a measure of the average kinetic energy of the molecules. The internal energy is flat out the total energy of all the molecules. So that's going to get measured in joules. Heat, strictly speaking, heat is supposed to refer only to the transfer of energy that's taking place due to differences in temperature. Officially, it's hard to stick to that definition. Now, if I take a bunch of molecules, what I could do is, and the molecules we're going to start looking at right here are fairly simple ones. They're actually not molecules, they're individual atoms. And so a sample of helium or neon or argon or krypton, those are what we refer to as monatomic gases. They're monatomic because the individual atoms don't connect, they don't form compounds with the other atoms. And so as a result, they exist as monatomic molecules or monatomic gases. And so for them, these are the easiest to think about because for these guys, the only possible energy would be kinetic energy of translation. There's no potential energies associated so much because there's no vibration, there's no rotation, they're just individual atoms. So it really comes down to the internal energy of a sample of helium comes down to what's the average translational kinetic energy, and then I multiply by the number of atoms, and that does it. Now, what we could do, since in chapter 18, we showed 1/2 mv average squared, that's 1/2 m VRMS squared, that's equal to 3/2 kT. So it says the internal energy for a sample of monatomic atoms is going to be given by 3/2 nkt or 3/2 little n big RT, where the little n is the number of moles. So that's a good reference place. We've looked at kind of the simplest collection of atoms we might consider. Now, if the atoms are monatomic, helium, neon, argon, krypton, then the energy of translation, n times the average value, that gives us 3/2 nkt. What if they're diatomic? What if they're O2, N2, H2, maybe CO, carbon monoxide? Well, in that case, what we find is these molecules with two distinct nuclei have two distinct mass centers. For the monatomics, rotation isn't even well defined. If I've got all the mass concentrated at one point, what would rotation mean anyway, quantum mechanically? But here, I've got a center of mass in the middle, and this molecule has a meaningful definition of rotation, and that would mean that the molecule could be oriented differently, and that makes a difference in how the molecule is how it's oriented, what axis it lies along. So this one could be oriented differently. This one, it's not clear. So we pick up an additional amount of rotational energy, and that turns out to be in the amount of kT. So I can take the 3/2 kT, it already has translational energy, but I can add in an additional kT due to rotation. Now, it's often written as 2/2 kT, which is a little funny, but what we're thinking is this is 3/2, and if I add 2/2 more, I'll have 5/2. So the diatomic molecules typically are going to be represented as having internal energies of 5/2 kT on average. Now, there's also the possibility of vibration, which means that the nuclei are vibrating. They're oscillating, they're vibrating back and forth around the center of mass, and that potentially can add in another kT, so that would be another 2/2. That would be 3/2 plus 2/2 plus 2/2 would be 7/2. But it turns out quantum mechanically that at familiar temperatures in the hundreds of kelvins, it is the case that most molecules are in the ground state of vibration. And to get to the first excited state of vibration requires a pretty good sized jump. And so at everyday temperatures, 3, 4, 500 kelvins, the vibrational quantum states are not populated. The excited states are not populated. So the vibration is something that could happen for these gases, but it won't until we get up to much higher temperatures, something like in the thousands of kelvins. Then we would have vibrational energy. So for the monatomic gases, because of the quantum state issue, the internal energies are entirely translational, 3/2 nRT, but for the diatomics, at familiar temperatures, they are going to be 5/2 nRT. So at the same temperature, molecule for molecule, the diatomics have more energy. And that's because they have energy of rotation, which the monatomics do not have. So the diatomics are more. Again, they're stating here there's rotational and vibrational energies that need to be taken into account. We just did. The diatomic gases, common examples, N2O2, COH2, those are all diatomic. Now, if I go to more complicated molecules, like carbon dioxide or water, those are considered polyatomic, and that gets more complicated. If I look at a polyatomic molecule, I'll continue to have rotational energies, but the rotational energy states are more difficult to calculate. I will also, as I get to more complicated molecules, I will have additional vibrational energy modes that come in. Again, that gets to be more complicated. So we're going to pretty much limit ourselves to monatomic and diatomics, and then we'll mention the polyatomics from time to time. All right, here we go. Let's take a look. So everything we just talked about was for gases, and now what we're going to do is we're going to take a look at how do we keep track of internal energies for solids and liquids, and those are more complicated. So the solids and liquids, in addition to kinetic energies, there are significant potential energies. There's the attraction that takes place between the individual atoms. So if I have a block of aluminum, there's a lot of potential energy associated with the attraction between those. Now, what we can do is we can ask a different sort of question. We can say how much energy would be required for these materials to raise their temperature. So let's go back and take a look at these formulas that we developed. For the gases, we said that internal energies can be directly related to temperature. So I can use these formulas and say if the temperature goes up, there's going to be this much additional internal energy. So those formulas enable me to go in and say, hey, if I have a collection of oxygen atoms at 20 Celsius, and I want to raise the temperature to 80 Celsius, how much energy do we have to put in? And I can just calculate it from those formulas. And these formulas, the upper formula applies to anything that's monatomic, and the lower formula applies to anything that's diatomic. And then we're done. So from a very theoretical basis, we are able to derive those formulas and use them. Solids and liquids are more complicated because of the attraction between the molecules. And that means rather than theoretically predict these are based on experimentation. So they've put these in calories. I'm ignoring the calories. I'm going to come over here to the joules column and just see what the specific heats are. Now, we could have listed these objects in terms of what we call a molar specific heat, but this table at least is a mass specific heat, and the formula looks like this. It says that if we want to see a temperature change of delta T, what we can do is take what we call the specific heat, multiply that by the mass, and combining all those will give me a value of heat. So remember, heat was the transfer of energy through temperature differences, and so this is the amount of heat coming into the sample in order to raise its temperature. Now this is in terms of mass, but the formulas we did for the gases are in terms of the number of moles. So we can work in terms of either one. Theoretically, it makes more sense to work in terms of numbers of moles, but experimentally, it's easier to work in terms of mass. Because if I'm in the lab room and I measure a sample, I set it on the scale gives me the mass. If I want to get the number of moles, I have to find a periodic table and convert those masses into moles. My personal preference is to do everything molar to see a more useful comparison of one material to the next. So for example, if I look at aluminum and iron and lead and silver, if I look at a bunch of metals and I look at the specific heats, they all look so different. And I'm thinking, wow, these metal samples are so different from each other. But if I do the same thing in terms of molar specific heats, I find out they all have very similar values. And I go, oh, they're not so different. Every metal behaves like every other metal. It just comes down to the number of molecules. So anyway, this is our formula, and the big Q here is heat. So that's what we have to remember now. Big Q is heat. It's thermal energy being transferred through a difference of temperatures. So that's our formula. Let's see if we can try this out. It says here, let's see how much heat is required to raise the temperature of 20 kilograms of iron from 10 Celsius to 90 Celsius. Now what happens if inside that iron container we fill it with 20 kilograms of water? So 20 kilograms of iron, 20 kilograms of water. I can look these up. So we're going to go from 10 Celsius to 90. That's a delta T of 80 Celsius. It's also a delta T of 80 Kelvin. This is the formula to calculate specific heat transfers. Now C itself is the specific heat, and that's coming from the table. So if I go back and look at the table right here, here is iron. Iron says that the specific heat, little c, is 450 joules per kilogram per Celsius or per Kelvin. Water is, this is joules per kilogram. Okay, this is 4,186 joules per kilogram per Celsius or per Kelvin. So I'm reading these off a table. And what I find is that for the iron, this is M, C delta T. And the amount of heat I need to add to that iron is 720,000 joules, 720 kilojoules. So I got to check units here. So what happens is sometimes it's going to be grams, sometimes it's going to be kilograms. If I miss that, I'm off by a factor of 1,000. Sometimes this is going to be joules, other times it's going to be kilojoules. If I miss that unit, I'm off by a factor of 1,000. And as I've mentioned before, I think these factors of 1,000 are so important practically. You know, if you're a physician or some kind of a, if you're a physician and you prescribe something but you get it wrong by a factor of 1,000, that's significant. So I tend to emphasize that fact, and then I also, when I'm grading midterms and such, I do take off a fair amount if the answer is off by a large factor. You've got to be able to catch errors like that, and sometimes it's difficult, I understand, but other time, but you have to do your best to try and avoid factors of 1,000, or even a factor of 10 or 100, but a factor of 1,000 or 1,000,000, those are going to be important in whatever profession you end up in as a scientist or as an engineer of some sort. So those are going to be really important. Again, the water that we put inside here now is 20 kilograms. These match because they told us they match. This is iron, this is water. The specific heat's different. Water has a really high specific heat. It's at 4,186 joules per kilogram per Kelvin. There's a temperature difference here of 80 Kelvin. That means that the water would require 6.7 million joules. That's a lot larger. Now, I made a big deal about, I always like looking in terms, at the specific heats in terms of molar specific heats. And so water, the molar mass for water is 18 grams per mole. The molar mass for iron is 55.85 grams per mole. So in the sample, that 20 kilograms, it turns out 20 kilograms of iron is 358 moles. The 20 kilograms of water is 1,111 moles. So there are many more atoms of water in the 20 kilogram sample than there are iron. And so the molar masses, the specific heats rather, are a little misleading, so I converted that into molar. So if I did this in terms of moles, the specific heat for water is 75 joules per mole per Kelvin. The iron comes in at 25.1. All metals come in and around 25 joules per mole per Kelvin, because all metals have vibrational energies, and they have the same number of vibrational energy modes, so they're all very, very similar in terms of the molar specific heats. So again, even when we correct for the number of atoms, atom for atom, molecule for molecule, a water molecule has 3 times the specific heat as iron. So that tells me that water has many more things it can do with that energy than the iron can. Okay, so those are attractive forces within the between the water molecules, hydrogen bonding, vibrational energies within the H2O bonds. All that stuff comes into play by being 3 times as much. Okay, so how are we going to do measurements like this? We operate using something we call calorimetry. The idea is to isolate the samples and then say that within the samples, because energy is conserved, I can look at which samples are losing heat and which samples are receiving the heat, and I can set those equal. So here's a picture of what a calorimeter might look like. This calorimeter is using water within it. It's inside an insulating lid, an insulating chamber. Everything is trying to make sure that no thermal energy transfer occurs between the environment and whatever samples we place inside here. Now the water, the idea is to take something maybe at a high temperature, place it inside, and see how much the temperature of the water goes up. Let's look and see how that, I mean, we're doing this in lab, so you guys will get a chance to see this very directly in lab. Let's see how this works. So it says that, you know, an engineer, scientist develops a new metal alloy and wants to find out what its specific heat is. So it's a 150 gram sample that of the alloy is heated to 540 Celsius using some process, and then that sample is transferred quickly into the calorimeter, and inside the calorimeter are 400 grams of water, and it's starting at 10 Celsius. The calorimeter, it says, also consists, the wall of the calorimeter, 200 grams of an aluminum cup. So, and then it says the final temperature is 30.5 Celsius. So if we come back and take a look at the calorimeter that we have here, what it's saying is, see, there's this aluminum cup that the water is inside, but that aluminum cup is on all this insulating material. So when I put the iron sample, or the alloy sample, inside, the water heats up and the calorimeter cup, the aluminum cup, heats up, but we're assuming none of the heat transfers to any other parts of the calorimeter, none of the heat transfers to the environment. Okay, here's what the problem looks like then. Here is my metal alloy starting at a temperature I'm going to call Tx. Ooh, X sounds like it's a newly discovered metal alloy. And here's the mass. And then I have some water inside a calorimeter. The temperature of the water, I need to know the starting temperature. I need to know how much water is in there, the mass. Now I also need to know the temperature at which the aluminum calorimeter starts, but that's going to be the same temperature as the water. So Tc and Tw, those are the same thing. I need to know the mass. And I need to know some specific heat. So X is for the sample, W is for water, C is for the calorimeter. Let's take a look and see what heat is gained. So I place the metal alloy inside, and the water heats up, and I can calculate the heat by taking the mass of the water, the specific heat of the water, and then the final equilibrium temperature. So the initial temperatures were the Tx, Tw, Tc. The final equilibrium temperature is just T. And that temperature went up by 20.5 kelvins. Here is the specific heat of water in joules per gram. Notice it's 4.186 now because I'm using joules and grams. This is 400 grams. The heat that comes into the water is 34,325 joules. So I know all the information needed to calculate how many joules of heat transferred into the water. I can do the same thing for the aluminum cup. Inside that calorimeter, that's the mass times the specific heat times the temperature increase, same temperature increase. Specific heat is different, the mass is different. This is only 3,690 joules. So by placing water in the calorimeter, remember water has a really high specific heat, so the water is able to absorb a lot of heat without having its temperature change by very much. So the water took in 34,000 joules plus, you know, some change, and the calorimeter took in 3,700 joules. I can add those together. If I take this heat and this heat, what I'm assuming is all of that came from the metal alloy while it cooled down. So let's see how that works. The heat lost, that's the metal alloy, and that's going to be equal to QW plus QC. So once I've calculated the heat gained in the water and the aluminum cup, I can now see how much heat left the metal alloy during its cooling process. Now that's going to be equal to the mass times the specific heat times the temperature variation, and I can take that equation and say that the specific heat of this newly developed alloy is the heat that came in divided by the mass divided by the amount that it cooled down. Now, did we get this right? I got to check this. This is the heat that came in. This was its mass. What was the starting temperature? Oh, 540. Yeah, so it is 540 Celsius that it started at. So the temperature went from 540 Celsius down to 30.5, and that's a difference of 509.5. This can be listed in Kelvin or Celsius because it's a delta T formula. And carrying out all the calculations says this metal alloy has a specific heat of 0.497. So that's very similar to iron or steel. Iron and steel has a very similar specific heat. Maybe it's an alloy of iron of some sort of a new steel that they have developed. So specific heat calculations like this, very important. You're going to see examples of this, not just here, but in the homework. As always, make sure you're going through all of the examples we look at. Make sure you're going through all the homework problems. And you're getting to a point where you really know your way through. You can move through the problems pretty quickly. Usually that requires solving them more than once. Okay. And it certainly involves more than just being in a room where somebody is explaining that to you. You got to go in individually and make sure that you've developed your own set of skills in problem solving, and you can get yourself through these problems in a timely manner. Okay. Let's see. Here what we're doing is we're taking a look at adding energy. Now it says in kilocalories. Oh my gosh. Okay. And then what happens to the temperature? So let's say we start at a temperature of -40 with some ice, which is made out of water molecules, and then we start to add in, we start to heat it up. So energy is being added in through heat, and what's happening is the temperature of the ice raises until it gets to 0 Celsius, and then I keep adding heat, but it's not raising its temperature anymore. The energy is going in, no temperature effect. Instead, it's that phase transition. So we talked about this also in chapter 18. When we hit a phase transition between solid and liquid, we have to put energy in to allow the water molecules to separate from their locked position that they're in, their structured position as a solid, and free them up a little bit so that they can move freely past each other. And so this amount of energy that goes in, that's referred to as a latent heat. And then once it's all water, again, as we add energy, as we add heat, the internal energies are going up and the temperature is going up. But then we hit vaporization. Now if you take a look at this scale, look how much energy is required to vaporize water molecules. That's a lot. So water molecules require a huge amount of energy to separate them from liquid into individual molecules that make up a vapor. So that's another latent heat. So there's a latent heat here, there's a latent heat here. Let's go in and see how to include phase changes that take place. So here are the latent heats. Now, when something melts, when it goes from solid to liquid, we call that the melting point. The latent heat is referred to as the latent heat of fusion. Kind of an interesting term. When we have vaporization take place, something at the vaporization temperature or the boiling point, the heat of vaporization is called heat of vaporization. So these are the latent heats that's either for fusion or it's a latent heat of vaporization. And just looking across the table quickly, here's water. So water melts or freezes at a temperature of 0, and the latent heat of fusion is 330 joules per gram. When water vaporizes, that process takes place at 100 Celsius, but that process requires 2,260. So the latent heat of fusion for water is large. The latent heat of vaporization for water is really, really large. That's a good thing, you know, because the heat of vaporization is so large. I think I mentioned before, when I'm cooking, that usually involves just boiling water and putting something in boiling water. That's my definition of cooking. And so what happens is, I get out a pan and I put some water in it, and I turn on the I turn on the range top so that the water is going to heat up, and then I walk out of the room and I completely forget that I'm cooking. And so what happens is this: the water raises its temperature, and within a few minutes it's boiling. Now the boiling process doesn't take nearly as much time as the vaporization process. So that's what saves me, because if the heat of vaporization were smaller, I would scorch every pan that we own. But fortunately, the heat of vaporization is so large that when I put some water in a pan and I forget about it, it's going to take like 20 minutes at least until all that water is gone and the pan begins to scorch. So I have like 20 minutes to remember that I left some water in a pan being heated on the range top. So heat of vaporization helps me out a lot, that big heat of vaporization, so I don't scorch all the pans. This is the formula for heats of vaporization. It's pretty easy. Q is equal to ml. So what I have to do in a problem, well, let's take a look at a problem about ice melting. So what this says is I have a 500-gram chunk of ice. It starts out at minus 10 Celsius. So sometimes students go, wait a minute, if it's ice, isn't all ice at 0 Celsius? And the answer is no. It's solid from 0 Celsius all the way down to absolute 0. So you've got a wide range of temperatures possible for ice. And this ice is at minus 10 Celsius. And we're going to put that in 3,000 grams of, now they call it iced tea. It's just water. So iced tea is basically water. But we're putting some ice into some tea that is at 20 Celsius. And the intention is we want the ice to bring the temperature of the iced tea down so that it's at 0 Celsius. If I've got if I'm drinking something, it's a hot summer day, and I've got, which never happens in the Bay Area. You have to go outside the Bay Area to experience a hot summer day. But if you go to, you don't have to go very far. You can travel over the hills. You can go to Vacaville or Davis or something and experience these temperatures in the hundreds. So I want the iced tea. I want to be able to put ice in and have some ice remain. As long as the ice is still in there, not all the ice has melted, and I've given enough time to reach thermal equilibrium, that guarantees me that water, or that iced tea, or the Diet Coke, or whatever is in there, is at 0 Celsius. And that's the temperature I want. So I want the ice to bring the temperature all the way down to 0 Celsius. So the question here is, if I put in 500 grams of ice into 3,000 grams of water at 20 Celsius, will all the ice melt? What's the final temperature going to be? Is that going to bring it right down to 0? Or are we going to come up short? Is all the ice going to melt and it still is not at 0? Let's check and see. So phase changes make these problems more complicated. As you may already be thinking, wow, I've got more steps to keep track of. So this one, you do have to set this up more carefully. I drew a diagram. Here's my ice. It's at minus 10. Here is my initial water sample at 20 Celsius. I'm going to combine these. Now, we're assuming, even though I'm not making iced tea in a calorimeter, we're assuming all of the heat transfers take place between the ice and the water. So we're going to treat it as if it's in a calorimeter. There's going to be a final equilibrium temperature. Let's find out what it is. Here are the formulas I'm going to need. For each of the specific heat processes, I need MC delta T. For each of the latent heat processes, I need M times L. That's the deal. So let's see what happens. Let me take the water sample first. I'm hoping that I can bring that all the way down to 0. I don't know that's going to happen, but I have to start making some kind of assumptions. So let me assume that the water comes all the way down to 0. That would be 3,000 grams of water, specific heat 4.186 joules per gram, and a temperature difference of 20 kelvins. That means I have to take out 251,160 joules. That's how many joules of energy need to be removed from the water to bring it to 0. Now let me do the same thing with the ice. If I take all the ice and raise it up to 0 Celsius, that's going to require 10,500 joules of energy. So here's the 500 grams of ice. Here is the specific heat of the ice, 2.10, not the same as liquid water, and it's a 10 Kelvin difference. So that's not enough. So what's going to happen is all of the ice now is at 0 Celsius. All of the water is at 0 Celsius, but the Q's don't match yet. Now I have one more place I could get some energy transfer taking place, and that would be melting the ice. So I'm going to take the 500 grams of the ice, the latent heat for fusion, 333. If the ice melts, that will draw in 166,500 joules. It didn't work. The ice melting and the ice raising its temperature to 0, and a second process of the ice melting combined only takes in 177,000 joules. That's not enough. I don't think I added these right. Oh, I did. Okay, I see it. That's not enough. So what happens is this. I've got water, which is at 0 Celsius. I've got ice, which melted, and so that's now at 0 Celsius. But the energies don't match up. And so what I'm going to do is I'm going to take the Q and say, okay, I released 251,160 joules of energy and brought the water down. The ice raising its temperature required 10,000 of those joules. The ice melting required 166,000 joules. I still have 74,160 joules remaining. What am I going to do with that? And what I can do is I can take the entire sample of water, 3,500 grams, I can put the heat back in and use the specific heat of water to determine how much the temperature actually will be. And what that tells me is the final sample is 100% water. The ice is melted now, everything's liquid, and we only were able to bring the temperature of the iced tea down to 5.1 Celsius. We're going to need more ice, right? 5.1 Celsius is not tolerable. It's a really hot summer day. We're going to have to get that iced tea down to 0 with some leftover ice in it. So we need more ice is the answer to the problem. All right, if I'm doing solving problems using calorimetry with specific and latent heats, we have to do all the things that we just did. So this is kind of outlying. We're assuming that the system is isolated. We're using conservation of energy. We're using specific and phase and latent heat processes. We need to do both. And we kind of have to piece these problems together. And so as we saw, we had to go in and start making some assumptions. And when those assumptions didn't work entirely correctly, we had to go in and find out how much additional heat or how much heat was missing, and then apply that to the whole system. And that's just the way it works with latent heats. You can't up front write down the formula with the latent heats because you don't know if the latent heat is going to apply to the whole sample or not. All right, so that's a good problem to consider too. This would be a very interesting problem. Let's say you go back and you retry it and you get comfortable following this through. Change the amount of ice. So what you could do is go from 500 grams to, let's say it's 1,000 grams of ice. Well, what would 1,000 grams of ice do? And that would be twice as much heat. That would be enough to bring the water to zero. And then you'd have to find out how much ice didn't melt. So try that as an example. All right, and then this is talking about how we carry out these processes. All right, more stuff on the latent heats. Let's talk a little bit about internal energies. So now that we've looked at all these different phases, let's talk quickly. I guess we just have a few minutes left here. If I have a diatomic gas, N2 let's say, and it's got an internal energy of 5/2 nRT, what that suggests to me is as the temperature drops to 0 Kelvin, there will be no internal energy, and that seems fine and good. I can do an internal energy versus temperature graph, and the water is just going to, the line here is just going to be something that follows the nitrogen molecules right down to absolute zero. What's the complication here? Oh yeah, the phase changes. So I can use that formula very reliably and calculate, let's say we have a sample of 1 mole of nitrogen, that would be 28 grams. If I have a sample of 1 mole and I use that formula, I can use that all the way down to the liquefaction will take place at 77 Kelvin. So once I get down to 77 Kelvin, it turns into a liquid. That's a problem. So now I plugged numbers into this formula and found out when I get down to 77 kelvins, this 1 mole sample has 1,600 joules of internal energy. So that's the internal energy that we have for this collection of nitrogen molecules that are acting independently, and that takes into account their kinetic energies of translation and rotation. Now what happens though is now there is a latent heat, and a latent heat involves potential energy. It involves attractive forces between the molecules, and that means my internal energy drops. When we go from vapor to liquid, that lowers the internal energy. That energy is given off somewhere. I've placed the nitrogen in a really cold region, and now the nitrogen goes through a phase change and releases all of this energy as the nitrogen molecules come together and stick to form a liquid. Now I looked up that heat of vaporization. It was 200 joules per gram. I used the nitrogen molar mass to find out that is 5,600 grams per mole. So now what that's saying is, once the nitrogen liquefies, the potential energy has, the internal energy has gone negative. I started out at 1,600 joules of translational kinetic energy, rotational and translational, but now because of the phase change and the energy being taken out during that process, I am now at a negative energy, and that's how we do it. That's how we think of the effect of going through a phase change. Back here we had these gas molecules. They were independent gas molecules, not interacting with each other, and so that's a good reference to use, and we were on our way to bring the energy right down to zero using that formula, but instead a phase change took place, and that took us into the negative energy regions. So once the 1 mole has liquefied at a temperature of 77 and it's 100% liquid, the internal energy is now minus 4,000 joules. Okay, so we can use minus numbers. We saw this with gravitational potential energy, and now we're seeing it with electric potential energy, electric magnetic potential energy between the atoms and molecules. So this number goes negative. Now, if we continue to take energy out, it turns out that the liquid freezes at 63 kelvins. So at 77 it liquefies, at 63 it freezes, and so what happens is during that process, again, energy is going to be taken out. I looked this up. I got some numbers that I couldn't see consistent numbers. I picked ones that seemed most reliable from online. It seemed like the specific heat for liquid nitrogen is 56 joules per mole per Kelvin, and the specific heat for solid, frozen nitrogen is 44. I also found some really nice images of frozen nitrogen on some of the outer planets. I think it was Pluto. They had some images taken by the, what was it, the New Horizons spacecraft or something. Anyway, they had pictures of Pluto, the surface, really nice pictures of frozen nitrogen on the surface. Okay, because it's below 63 Kelvin. All right, so here's a phase change. We drop negative, and then we continue to take energy out. At some point, we hit another phase change. The energy drops even lower, and then the rest of the way to absolute zero, we continue taking energy out at a rate of 44 joules per mole per Kelvin. We can add all those numbers up, and that would say at absolute zero, the internal energy is not zero. It is this way negative number, and that's because of the way we've defined potential energies. Okay, so at absolute zero, the energy bookkeeping actually says the energy is this very negative number. Okay, that seemed like something that I thought would be useful to throw in, to think about how all the potential energies and the attractive forces are related to the kinetic energies. Now that's going to be a good place for us to stop. So I'm going to go ahead and stop there. If you guys have any questions on the stuff that we've looked at, we're kind of headed into a new part of the chapter. So I'm going to stop right there for the break.